In this demonstration, we start by importing ECAD schematic data using an associative bidirectional data exchange for printed circuit boards. In PCB Exchange, therefore, now we're going to go ahead and select the PCB board file, and we're going to filter out some entities. In this case, we want to remove some of the holes that are probably too small to worry about, and essentially simplify the model, the 3D model. We can go ahead and say OK, and this allows us to directly generate a 3D assembly of the board and its components. We're able to do this because this 3D information exists in the 2D ECAD software that we're able to convert into 3D. We are now ready to create the ESC model, or the simulation model. By pointing to a user database of component thermal properties, Simcenter 3D creates a suitable model for each electrical component. Again, here we choose to simplify the model in preparation to generate the simulation model. While this is being generated, we should note that the copper trace data imported from ECAD is used to compute and apply detailed conductor properties to the board thermal models. If you recall the workflow I described in the previous slide, this is where the automatic computation of the spatial thermal conductivity comes into play. Additionally, it is the ability to have a lumped representation of the components on the board that allows for the rapid generation of the CAE model. Now that the PCB finite element model has been generated, it can be added to the finite element assembly of the PC chassis. This is simply done by using assembly modeling techniques identical to CAD, where we can add the PCB as a component into the assembly. We can quickly hide components from view for clarity's sake and position the PCB. There are any number of ways of doing this, even with assembly constraints, but here we position with the origin of this coordinate system and give it a direction. We then need to generate the internal and external air domains necessary for thermofluid analysis. In a typical CFD workflow, developing the fluid domains can be very time-consuming. However, with Simcenter 3D, this can be easily done using the surface wrap algorithm. In this case, we first select all the geometry that we want to do the wrap around and decide if we wanted it to be an interior or an exterior wrap. In this case, we choose to have an interior wrap, and we just choose a point somewhere in between, in the middle, from one side to the other side of the component. You can see the orange point. Once we have defined the internal volume, we then just need to give it a resolution, a global resolution for the wrap. However, we can choose to further refine the wrap by defining a tighter local resolution. In this case, around the PCB. This flexibility ensures we produce a mesh that captures details only where needed and does not unnecessarily increase computation time. Because components of the PCB are close to those of the assembly, we can use contact prevention constraints to ensure an adequate gap is maintained. In this case, between the gray component at the top and the two chips below. We select the first one, and then we create a second contact prevention constraint on the second one. All these constraints can then be added to the surface wrap definition. And finally, the resulting fluid domain is associated to the base geometry, so in the event of a design change, you can rapidly update the fluid domain with little additional effort. In this case, we chose that the wrap automatically generate a 2D mesh. This 2D mesh is then going to be used to only generate a corresponding 3D solid mesh using the solid from shell command. We also define the material properties for this volume, which of course is air, and we can then generate the 3D mesh. But one of the key points here is that by maintaining associativity throughout, at any time, if the PCB design changes, the wrap, the 2D and 3D mesh will always automatically update. So once the internal domain is generated, we can then generate the external air domain around the enclosure. In this case, to define the external air domain, we need to have the volume that represents the external air. And this is easily done by having an existing FEM file that we just add into the assembly as we did before. And this body, this geometry, represents the external air around the PC. This PC, we should note, is a rack-mounted PC, so therefore the air is the air that would be represented inside a data center. So again, we use the same surface wrapping algorithms to generate the surface wrap, which generates a 2D mesh, and of course then we generate the 3D mesh as well. Now that all the meshes have been defined, we can go ahead and generate the simulation file, where all the loads and boundary conditions will be defined. We select from the template for the ESC solution, click OK, and generate the new simulation file. Of course, what we're going to be doing here is generate a coupled multi-physics thermal flow analysis, as can be shown in the analysis type. We then need to set a number of different variables, and we take advantage of the parallel processing capabilities that are available to us by using some high-performance computing. Set a few additional variables, and of course we need to set some result options to ensure what type of results we wish to see, what type of output requests we would like to have generated. Finally, we just need to generate or define the direction of gravity, which in this case is in the -z, and now we've fully defined our solution. Because the CA model for the PC chassis is an assembly, we can quickly reuse existing boundary conditions. Here we can import previously defined boundary conditions for the PCB into the entire AFEM. This greatly reduces pre-processing time by not having to redefine loads and boundary conditions at a new level. To ensure that we don't unnecessarily clutter the simulation navigator, we can also quickly do some bookkeeping and select all the different entities we've just generated and put them into a new folder. To complete this model, flow boundary conditions are applied, in this case at the inlet, to represent a forced airflow of 5 meters per second from the ceiling onto the PC, which again, as I said before, would be rack mounted. The flow outlet would then be on the floor, which is typical of a data center setup. Once the model has been solved, we can view the results to see whether this nanobox PC dissipates the heat generated from the PCB, or whether a redesign is warranted. We can first observe that the airflow at the top flat surface of the PC is close to zero, which is expected since the air from the ceiling hits the top of the PC. This is also a good sanity check of our model. Then we observe that the air accelerates along its fins to the side. We can then view the thermal results of the PCB and see that there is a high temperature of 51 degrees C, which is mostly localized on the board. The corresponding components, however, remain at the ambient air temperature, which indicates that the heat is being well dissipated, even within the PC. This is confirmed when we look at the internal fluid temperature and see how the heat is transported away from the PCB inside the enclosure. While these results indicate that the mechanical design will meet the operating conditions of this PCB, it is also possible to quickly create and evaluate multiple PCB design variants and compare the performance of each. With traditional CA tools, this would be a tedious task that could take days. But through Simcenter 3D's fully associative analysis model, we can quickly update the analysis model to reflect each of the new design variants within minutes. Now, going back to the assembly model, we are able to replace the PCB component with a new board. When replacing the board, Simcenter 3D will automatically position the new board in the same location as the previous board. You can then observe that the air domains are out of date. However, by quickly redefining the surface wrap constraints for the new board, and then dragging and dropping the constraints into the air domain recipe, the wrap and resulting air domain get updated to the new design. Next, we re-import the loads and boundary conditions for the new PCB into the assembly model and resolve the model. Finally, we wish to compare the thermal performance of both PCBs, and this is easily accomplished by displaying both results side by side and interacting with them simultaneously. I hope this demonstration gave you a sense of the unique end-to-end workflow that can be achieved for the electronics industry with Simcenter 3D. Now let's take a look at a few customer success stories with this solution.